Over the past few months, many people have asked me about my KiCad workflow and how I generate documents such as these schematics that you can see on the left here, or how I generate fabrication documents such as uh, the one you can see on the top here, or assembly documents that you can see on the bottom right. So in this video, I will be explaining the plugins that I use, as well as the different tools and the entire procedure of how to generate these types of documents. I will also briefly go through how I organize a project in KiCad, so about the folder structure, as well as tips and tricks for making your schematics look better, and so on. This video will also rely on a custom KiCad template that I will be sharing in the description, so you can have a look, and you will have a link to this GitHub repository, which you can load in KiCad as a template. So first, in order to get the template, you will need to go into your template folder. Here in Windows, it is under the Share, KiCad, and Template folder. So what you can do is just get the link in the description and just clone the repository. So just copy that, and if you have a Git, you can just do git clone and paste this link. So just note that here I am running the command prompt as an administrator so that I can clone this repository with the access rights. So just clone it and type in my GitHub password. Once that you have cloned the repository, you can simply open it as a template. So I will create a new project from template, and then I will just select the correct folder. So here I will go in my template folder and select the KiCad templates. And this is going to be the KDT hierarchical template. So just press this, and here you can see the custom template. Let's save this into a folder that we will call something like example. Once you have created your project with the template, you will see here all of the predefined folders that I personally use in most of my projects. So for example, we can see here in the Amulet controller project, which follows this same template, we have the computations where I put every computation that is needed to understand this project. Here it is an Excel sheet, for example. In the DXF SVG folder, I will put all of my vector graphics. In the images folder, I mainly add pictures that are either used in the schematic or things that I want to add in my GitHub repository. Then in the logos section, I will just add different logos that are needed. The manufacturing folder contains two subfolders, one for assembly and one for fabrication. The assembly one contains the bill of materials, the Centroid files, as well as the assembly document. And the fabrication folder will contain the Gerbers, and they will also contain the assembly and the fabrication document. So this really depends on what you want to give to the manufacturer. This is not really needed in this folder. I will also have a zip of the Gerbers, and this is optional, a CSV file indicating the position of all of the test points. So there are also other folders, such as the schematic folder, where I just plot my PDF of the schematic, and the step and blender folder, where I add the step file and blender files for 3D renders or for integrating with a mechanical CAD. The template folder contains the different templates that are used to define the schematic blocks. So this is the block that you see on the bottom right of the schematic. And there are also other files which are predefined, such as the git ignore. So this lists all of the files that are not needed in the GitHub repository, but there are also other files which I will explain very shortly, such as the custom design rule file. This is the KiCad DRU file, but there are also board to PDF config files and bill of materials config files. For the library management, I strongly suggest only using local or project-specific libraries. So if I go in the symbol editor, for example, here you can see all of my custom libraries. I like to prefix them with a 0 so that they appear at the top. And all of these symbols are custom and they are set as a local library. So why local? This is because this allows us to share the project a lot more easily than if it was a global. So I usually just have a lib folder here, and I then have two subfolders, one for the symbols, where I set all of my libraries for the symbols, and then I mirror the names with the footprints, and in each footprint library, I add all of my footprints. The 3D models is simply here to add the 3D models, and they are either downloaded from the internet, generated from Altium, or modeled in Fusion 360. So first, I will be just showing you how to make it look like this. So here you can see that the font is not the default KiCad font, and the colors are also a bit different. So if you go in your preference, here you can select your font in the display options. I really like to use the Times New Roman because it kind of looks like Altium. And if you go in the colors, you can also choose your theme. So if you go in the theme folder, you see that I have a custom Altium theme.json, which is in this particular folder. And this JSON file can be found in the KiCad template that you just cloned before. So you can just copy this file in this folder and load it. Before going into the schematic, I will just show you what you can change for each project using this template. So this template uses what is called text variables. If you go in the schematic option on the top left and you go in the text variable option here, you can see the different fields that you can change for your individual project. So these fields will change the different sections here. So for example, if I go here and I change the amulet motion control to something else, it will change it also. Okay, so now let's go through a schematic that I consider is pretty good. So this is the schematic for the amulet motion controller that I've designed. And this is also using the template that I shared at the beginning of the video. So you can see a proper application of that template. So what I like to do in schematics is to first have a table of contents. So this is useful if you have a fairly large project. This can really help having a nice overview of what sheet does what. In this table of content, I will have the title, the variant version, the revision, the date, as well as a top and bottom view of the PCB. And there will also be some indication about the different types of comments that will be used throughout the document. The second document that I find is maybe one of the most important one is the block diagram of the project. I think that every complex PCB has to have this type of diagram in order to really be able to understand the entire project as fast as possible. So this diagram is done entirely in KiCad, which is maybe not optimal. You can see here the different types of rectangles, but maybe a better way would be to generate these types of diagram in another software and import it as a vector graphics in KiCad. So here you can just see in the template that I've also put a very small example of how to make a block diagram in KiCad, and you can simply copy and paste these blocks to make your own. A very useful thing in KiCad is also the fact that you can set hyperlinks in the different fields. So if you go inside of that field, here you will be able to put the page number, which is very useful for navigating the entire document. There are also other types of documents that you can provide. For example, the power sequencing document. This is a bit overkill for this project. but in other more complex projects, such as FPGA boards, which require very precise power sequencing timings, it can be very useful. So I recommend adding these for any complex project if you find it useful. There are quite many ways to structure your KiCad project, such as flat schematics or hierarchical schematics, or just having everything on the same page. And the choice of which structure suits the project will really depend on a case-by-case basis. What I really like doing for more complex projects is a hierarchical schematic. So we will have different blocks, and each block will be connected to other blocks through hierarchical connections. They can be either a single wire transmitting a single signal, or they can also be buses which transmit an entire set of signals. Here you can see an example of what was done on the Amulet project. You can see that I dedicate 2 blocks to the microcontroller, one for the power and one for the input and outputs. And I have another 2 blocks for the power, other blocks for the sensing, interfaces, the motor control, and the user and miscellaneous stuff. Going into the microcontroller part, you can see how the signals are structured. So here I simply use local labels and define them in a bus, which is then transmitted to the project architecture, where I can connect the different buses to the other blocks. To create a bus, you can simply use this bus tool, which you can find here on the right, using this and this. And you can simply define your bus by putting this into brackets. Then you will need to go into the root part of your project, where you want to define the different connections. In this case, it's the project architecture, and you can simply go in the schematic options and go in the bus alias definitions. Here you can define the different buses and what members each of the bus has. An easy way to document your schematic is to add pictures. Here you can see that I added connector pictures next to each connector symbol, and this can really help the user better understand faster without having to go into the datasheet, understand faster what connector corresponds to what. This is very useful, and pictures can also be used for schematics. For example, in this case, I have a picture which shows what each connection corresponds to what type of feature, and it can also be useful to have a render of the board, so that we can see directly what board the schematic corresponds to. To add a rasterized picture, which is a picture with pixels, you can simply use this tool here on the bottom right, and you can then select your picture that you want to import. If you want to add a vectorized picture, you will have to use the import graphics tool, and here you can select an SVG, DXF, or other types of files. Aside from pictures, it can be also very useful to add comments to your schematic. In this template, I define 5 types of comments, so you can choose the one that corresponds to the severity of the comment, and also one for the layout node. This is very useful for documenting the schematic and to have a better communication between the person who handles the schematic and the person who handles the layout. Another important part of making good schematics is to make good schematic components. So what I usually do is to have all of the inputs on the left side and all of the outputs on the right side. So this can really help the reader, because usually you read from left to right. So you can really have a better grasp on what are the inputs and what are the outputs. Another useful thing that you can have is to split your component into 2 sub-components. For example, for the microcontroller, I have here a single component for all of the rails, the GPIOs, and I use another component for the power. And this can help by using two components because you can then, for example, here have all of the bypass capacitors on a separate section, which can also help in reading the schematic. Now I'll be just showing you how I add these 3D renders to the schematics. So this is a process that is valid for KiCad 8. I know that in the next version, which is KiCad 9, there will be a way to export these 3D models with a transparent background, but currently there is no way to do it. So you just go in View, 3D Viewer of KiCad 8. Here you will have your PCB. So what I do is I check the ray tracing option here. And I also like to toggle the orthographic projection so that everything is parallel. I find an angle that I like. So for example, this angle is okay. And then you need to change your background color to something that can be easily masked out. In this case, I will just change it to green. So just use this green here and do the same thing for the other one so we don't have a gradient. Like this. So now I just do File, Export Current View as PNG, or you can just zoom in a bit to have a better resolution. Maybe something like this is okay. So now just do File, Export Current View as PNG. I just save it here on my desktop. So let's call it AMOLED controller front. Once that you have saved your PCB render with the green background, what you want to do is to remove it before importing it into the schematic. So first we will add it to Photo P, which is a clone of Photoshop. So this is just in case you don't have Photoshop, but if you have Photoshop, you can also follow along. So I just import this file, then I go into the select option and I select the green part. I just click on the green part, press OK, then press delete to remove all of the green parts. Now just for some minor adjustments, here I also want to be able to remove this green part. So I will go into image adjustments and into the hue saturation part. I then select the green option and I can decrease the saturation of this part. So I will need to extend the range a bit in order to hit these green parts here. And I can also change the hue to make it a bit more yellowish in this case, if I want to remove these greens. So I can even extend it just a bit more, just to make, but I need to make sure not to affect the color of other things too much. Okay, so this looks pretty okay. So I just press OK. Then I will need to crop this. So I select this square select tool, rectangle select. I press shift in order to have a square. And then I just make a big selection. So it should clip to the bottom and top sides. Now that I have this selection, I can move it and I will just move it so it clips to the middle part. So here you should have some sort of cross forming, which indicates when you are in the middle. So I just do it like this. It's a bit tricky at first. Okay, so now it's in the middle and you can just do image crop. Now another important part is to remove these black pixels on the top and on the bottom. So just use this rectangle tool again, select this top part, then press delete and do the same thing for the bottom part. Now that you have removed the green background, you can simply do a file, export as, and save it as a PNG. So I'll just save this. And I now have this picture here, which I can import back into KiCad. So let's get into this template here. And to import it, you will want to use this button on the bottom right. So previously, I think I mentioned this import graphics option, but this is only for vector graphics. So now press this, select your transparent background picture. I'm not sure where it is saved. I think in the download option. So here it is. And now we can just reduce the size of it and place it wherever you want. Once you have all of your schematic well defined, you can simply plot it using File, Plot, and here you can select your KiCad theme that you want. In my case, it will be the Altium theme, and I want it in the color mode. I will plot it as a PDF so that I can have all of the hyperlinks. And usually I will have a dedicated folder, in this case, a schematic folder, where I plot the different, where I plot my schematic. So let's just save it as, let's just plot it and you will see what type of document comes out. Once you have plotted your schematic, this is what you should be able to see. So you have a table of contents where every link is clickable. And normally you should have the proper font and the proper colors that match the selections that you selected during the plotting phase. So there's nothing really new here. And if you are familiar with KiCad, this should be something that you should be already familiar with. Now I will explain to you how I generate the fabrication documents and the assembly documents. So first you will need to download the necessary plugins. You can simply go in the plugin and content manager, and then the plugin that you will need is the board to PDF plugin. So just install it and click on apply pending changes. And normally when you open your PCB, you should have an action plugin with the icon that corresponds to that plugin. So let's open the PCB. And here you should see the icon. So let's click on this. And normally, if you have the template, you should have this board to pdf.config.ini, which defines the different types of files that you want to plot. So basically what this plugin does is it allows you to plot the different layers of your PCB in a certain order and to assign different colors to each layer. In order to generate these types of files, you will need to add some information on specific layers on your PCB. So we'll show you how to do that now. It's a fairly involved process, but once it is done, you will be able to generate these files quite easily. So the most important layers are of the layers under the title page text layer. In this layer, I simply have these two texts here, which are used for the assembly document. Then I have the user comment here. This is simply used to generate the Blender 3D file. I will explain this later. Then we have the front do not place and back do not place layers. This is used in order to generate the do not place symbols on the assembly document. So if you zoom on this section, for example, if I manage to zoom on it, you will see here that we have a do not place cross. And in order to make these, it is quite simple. So you simply get, for example, okay, let's just do it with one of these components. So for example, with this resistor here, what I simply do is I create a rectangle which matches kind of the shape of that. Then I set it as on the correct layer. In this case, it will be the front do not place. And then I just get this tool to draw a line. And I do one line like this, one line like this. I can also reduce the thickness of these lines, for example, at 0.1. and set these on the correct layer. Here it would be front, do not place. And once it is on the correct layer, I can simply take all of this. So this, and this. Okay, and this, and just move this to the correct component that I want to mask. In this case, it's going to be that component. If I want to be able to, I just need to make it snap to the middle part here. And then what I like doing is to select both. So this component here, maybe just go in this mode, this component here, and then group them together. And now I have a single component which has the do not place symbol, and I can move it anywhere I want. So I just do that for every component that I don't want to populate during the assembly phase. And you can do the same thing on the back layer. So this is just as a way to, this is like purely for aesthetics for the assembly document, but I think it's quite useful. You can see on the front and on the back, it's exactly the same thing. The drill file layer is a very useful file which can indicate to manufacturer which type of hole is plated, which type is unplated, and what are the hole sizes throughout the PCB. In order to generate these types of documents, which you can see here, you will need to add this drill file to the PCB. So in order to do that, you can simply go in the file option, then go in the fabrication outputs, Gerbers, and you can go into generate drill file here. Here you will need to select the PTH and NPTH in a single file option and export it as a DXF in millimeters. I will simply export it in my Gerbers folder. So here I simply click on generate map file, and this will save the DXF at the correct location. Now I can simply do file, import graphics, and then I can select my generated DXF file. I will import it at a scale of 1. I like to set the default line width at 0.1 because some of these symbols can be quite small. The units is in millimeters, and the layer it should be imported on is the drill map layer, of course. And an important part is not to click on the fix discontinuities option, because otherwise it will mess up the drill layer. So just press on OK, and now you have this, which you can align with your PCB if you want. And then you can simply fill this table with the information that is given on the drill map. So this is how I create this layer, which is then plotted onto the fabrication layer document. The front and back test point layers are used to indicate the position of the test points as well as their reference designator. So you can see on the fabrication layer an example of how it is used. So here we will have our PCB with the different test points in red as well as the reference designator. These are searchable PDF, so it's quite useful if you want to know where is a test point. And here on the left, we will have the list of test points as well as its coordinates. So how do we get these test points on this layer? For that, I create custom test point footprints, so you can get them in the Amulet controller repository that I will put in the description. And you can see that, for example, for the back test point, we'll have this circle here, which is placed on user 3, and user 3 in this case corresponds to the back test point layer. For the front test point, we have the same thing on user 2, which corresponds to the front test point. And by using these custom footprints, we will have these shapes here on these two layers. Another very important layer for the assembly drawings are the fabrication documents. So we have the fabrication for the front and the back, and these define the dimensions of the components as well as their reference designator. Often in KiCad, you will see that there is a lot of text and it's very messy on this layer. This is because most of the times, if I add a resistor, for example, for example, this one, you will see that you have quite a lot of text. So on the front layer, usually you will have the reference designator, and then you have another text here. What I like to do usually is in my footprints, I remove this value text here. So if I go in my footprints here, you can see the different custom footprints that I have. You can see that all of these value fields here are hidden. And this is a very easy way to keep the schematic clean. And I recommend doing this in most of the components for the fabrication layer, because this text is often not very useful. I also like to add polarity or an indicator for the pin 1 on the fabrication layer, so that we can see on the final assembly file, we can see the polarity of each of the component. If you don't have custom footprints and you are using the KiCad footprints and still want something a bit cleaner, what you can do to remove or to hide these texts is to use the Edit Text and Graphics Properties tool. So if I go into this option here and I select the front fab layer, for example, I can select the value option here and set it to not visible. Then I just click apply, and you will see that every value text on the front fabrication layer will disappear. And then for this one, you can just put it inside if you want to have something a bit cleaner. Here it's a bit small, so I would put it outside actually. But for these components here, I set everything inside. The assembly text layers are very useful to add more information to the assembly document. So the assembly document is this one, and it can be useful for the manufacturer to know where to look for the bill of materials, or to know the number of components that is used throughout the board. So this is where I add this information, where I add the number of components for the front and back side, and also which type of component it is. Here, the assembly notes, you can change them as you'd like. This is just an example of assembly notes that I've used for this particular project. I also like to add the outline of the board on the right side for the front assembly, and on the left side for the rear assembly text layers. And this is useful in order to align a picture outside of KiCad in the document later on. So this way I can make sure that this picture is well aligned with this PCB. So how do you know the number of components for each side? So an easy way to do that is to install the IBOM plugin. So I'll just close this for now. And if I go in this project here, you can go in the plugin and content manager and install the interactive HTML BOM. Just apply the changes. Now, if you go in the PCB editor, you will have a new action plugin, which is here. So you can just press this. So normally, when you open this window here, it should already be loading the config file that is present in the template, which is the ibom.config.ini file. And this should configure this part of the export options. So I want to export this file in the BOM folder. Here it would be in the manufacturing, assembly, and IBOM folder. So I just click on generate BOM, and that will open this very useful assembly helper window. So I highly recommend using this for hand assembly, because you can simply check whether or not you want, whenever you place a component, you can simply check it, and you will be able to see it on the schematic what component you've placed. Another useful feature of this plugin is here in this window. You can see the different statistics of your board with what type of component, either it's SMD or through-hole, and the number of components for each type. And this can help you fill in this table here. The front and back dimensions layers are used, as the name suggests, to add more information on the dimension of the PCB. So I like to add these without any units and to just specify what units are used in the document. It is also useful to use these symbols here as a prefix in the dimensions. So this is this is more for the mechanical guy later on if he wants to design, for example, a casing for that. Can be very useful. I also add on this layer some more information about the stackup of the board. Here you can see an example. So I mentioned the material, which layer it corresponds to, the thickness of each layer, as well as the dielectric material, and also the Gerber extension file extension. In order to get this information, you can simply go either in your board setup where you define your stackup, but it is also possible to use the place tool here and to just place a stackup table. So I will place it here, for example, and I select the front dimensions. And I can use this information here to fill in this table. You can also just simply use that, but this doesn't look very good. And finally, you can add your fabrication notes. So this will depend on your project. Here, I'll just like to add some information about impedance control, like which layer is, on which layer I need impedance control and which is the reference layer. I also add some information about the design geometry minimum feature sizes, but this is more for just general documentation. On the front and back test point list layers, I have a list of test points as well as their net and the location in the PCB. So all of these locations are in relation to this origin here. So the origin was placed simply by doing the place and adding the drill place file origin here. So you can simply change it here, and this will give you the 0, point of each part of your PCB, like the components as well as the test points and so on. So I just add this here and also add these indications so that the mechanical engineer can maybe design some sort of bed of nails, for example, if he wants to do automated testing using these coordinates. To get these coordinates, you will need to do a few things. So first, going into the test point setting, if you go in the fabrication properties, you can see that the position file is excluded from the position files, which means that when you plot the position file, you will not see the test points. This makes sense as you don't really want to place the test points because this is not really a component and this is not a fiducial marker either. So what you can do in order to get these coordinates is to change this property. So I will just remove all of this. So just do this for every test point type. This is not the most efficient way to do it. There has to be a plugin that does that, and there's actually one that came out not long ago, but it is still in development. So I will show you the hard way. Once you've modified the footprint attributes, you can simply update them on the PCB. So what I will do is to go in Edit, then go in the Change Footprints. In this board, we only have the 0.5 millimeters footprint. So I will select this and update this. So only update the fabrication attribute. Now I click on Change, and it will change all of the footprints. I will do the same thing for the front footprints. And now click on change. And you will see here that if I select this footprint and go in the fabrication properties, now it is no more excluded from the position files. This means that we can plot the centroid file and get the coordinates of these test points. So now we'll just go in the fabrication outputs, then go in the centroid file, which is the POS file. So I will plot it as a CSV and use the drill place file origin so that it is being plotted according to this drill origin that we placed. So just select this folder, this random folder, let's say, for now. And now just generate the position file. So normally after generating the position file, you should have this file here. And if you open it, you will be able to see all of the components of that need to be placed on the PCB. Here we will also have some information about the test points. So I will be using this to fill in the table on the PCB. So I can just copy and paste these test points. So this is for the top layer. So I just go in KiCad here and paste this. Normally it should be exactly the same, as you can see. Then I can just copy and paste this section here, which corresponds to the nets. So I do it here. Here there might be a few issues because I don't know actually why, but maybe because Excel doesn't like pluses. So you can just manually correct these with VBAT or whatever. And here we will have the coordinates. You can use Excel also to reduce the number of decimals. Here I will just copy and paste it just to show you what can be done. And you can do the same for the last column. For the back side, it's very similar, but you will need to copy the values from the test points that are on the back. So in this case, these ones. And after this, you are actually done with all of the things to fill in order to generate these types of documents. Of course, you will just need to make sure to revert the footprints of the test points before generating the position file or the centroid file that you will give to the manufacturer. Once you've finished adding all of the necessary data in all of these layers, you can start generating the documents. So first, I will be generating the fabrication document. So the first thing that I will need to do is to go in the board setup here and to change in the text variable the type of document that I want. In my case, it will be the fabrication document. Once this is done, I click on the board to PDF symbol here. And normally you should already have all of these layers, which comes with the settings that comes with the template. So the only thing that you can do now, that you need to do now, is to click on the perform button. You can choose the directory here. In my case, I want to plot it in the fabrication directory. So just select like this. And I simply press the perform button here, and it should start plotting the document. You just wait for a bit, about 10 seconds or so, and you will be able to see the output. Once the plugin has finished plotting your file, you will find it in the correct folder here. And if you open it, you will be able to see the different things that it has plotted. So one thing that is missing, and this is because we have a limited number of layers in KiCad, is the name of what layer is what. So here I would like to add, for example, L1 signal plus power. Here it would be L2 ground or something. So I just do it on an external software. So I can simply open it in Xodo, for example. This is what I like to use now. So I just drag this in. And then to add some text, I just click on edit. I add a text box here. You can, for example, type in L1 signal plus power and set it in bold. And then I will just move it at the correct location. So you can change the font and everything by going here in this option. I think this looks okay, so I will leave it like this. And I just do this for all of the layers. For the assembly drawings, it's very similar to the fabrication case. So first I will go in the text variables and now change this to assembly. Okay. And now I will just go in the board PDF plugin here, and I will need to disable all of these layers. And instead, I will be adding some other layers. So the first one that I will be adding is the title page, then the assembly top, and finally the assembly bottom. Now I can simply click again on perform, but first I will just select the correct folder. Here I will put it in assembly and then click on perform. So this will give another file which you can see here. So this is again with the same name because you can change the name in the plugin. And if you open it, you will see a nice assembly drawing. And here there are the outline so that you can add the picture that you want to better illustrate this assembly drawing. To add the pictures to the assembly drawings, I just do it again on an external software, for example, Xodo. So I just import it here. And then here, for example, I like to add a 3D render of my board. So I'll go into edit and I will add a picture here. Here I can go in my folder, and in my images folder, I have different images that I can import. So I can just add this here and then do the same for the bottom side. And here I can do again the same thing for the top and bottom assembly drawings. So I just do this. Then this is for the bottom side. So I will put this on this side. Oh, okay, I just imported it on the wrong sheet. Okay. And now I just align this here somehow. And so let's say that I've aligned it well, and then I just export and save this file. So I really hope this video helped you generate some better looking documents with professional looking fabrication and assembly documents. There are not a lot of resources to do that in KiCad since it doesn't have a dedicated tool like Altium. So I really hope you will be able to adopt this in your workflow and tell me if you get any good results.